In this video, we're going to look at using some indifference identities of sine and cosine to verify other necessary identities. So this first one here looks at cosine of alpha minus beta divided by the cosine of alpha times the cosine of beta. And we want to verify that that's going to be equal to 1 plus tangent of alpha tangent of beta. It's important to understand that we can conclude now that any of these, we're going to start with just these four top ones, these four identities can be where we end. It's also true that we can utilize these within these verifying problems to get to something that we can work with. One thing that's really important that adds to the steps from your first section of identities is that we can now look at the insides and say, hey, listen, we have multiple different angle measures on the insides. Let's see if we can make the angle measures within those trig functions, if not be exactly the same, at least narrow it down to only a couple of options. So for this case, I have alpha, beta inside trig functions, and then I have alpha minus beta as one entity inside a single trig function. It might make the most sense to narrow this particular expression down into things that only have alpha and beta singularly inside of that trig function. In that case, I'm going to go ahead and use cosine of x minus y as my identity, where x is alpha and y is beta, and I'm going to rewrite that side of the expression into this right here. So cosine of alpha minus beta is the same thing as the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. This is all still divided by the cosine of alpha, the cosine of beta, and it's still supposed to be equal to 1 plus the tangent of alpha times the tangent of beta. Again, keep in mind, all I did was use this identity here to change this into this. The next step is, well, now that I have removed one of the more complex interior angle pieces, or I've taken it and I've said, well, let's just tear it apart into singular alphas and betas within trig identities or equations, expressions, I can then go ahead and do all of my same basic algebraic skills that I learned in the previous sections. The first thing that I'm going to notice for this example is that I can take this denominator and I can distribute it to both of these expressions. So that means I'm going to have the cosine of alpha, the cosine of beta, divided by the cosine of alpha, the cosine of beta, plus the sine of alpha, the sine of beta, divided by the cosine of alpha, cosine of beta. This is still equal to this other side. I'm not going to modify this side. I'm actually going to leave it alone. So I'm going to go ahead and not write anything down here, just to emphasize that I'm not changing that side. Over here, I can group multiplication and divisions as long as there's no addition or subtractions individually. For instance, it's cosine of alpha times the cosine of beta divided by this, but I can instead take the cosine of alpha and divide it by the cosine of alpha and separate that as a multiplication from the cosine of beta divided by the cosine of beta. Again, I can reorganize multiplications and divisions in any order that I feel is most appropriate until there's an addition or subtraction sign. That's going to throw everything mathematically into a loop. Again, I couldn't do that here until I distributed that division. So cosine of alpha divided by cosine of alpha is 1. Cosine of beta divided by cosine of beta is 1. And technically this is then 1 times 1. So I'm just going to write 1 here plus. I'm going to do the same thing with this stuff that I did back here. I'm going to group the sine of alpha with the cosine of alpha. And remember that sine over cosine is tangent. It's only true if the angles are the same. So if I tried to group the sine of beta with the cosine of alpha, this wouldn't actually work. It wouldn't make any sense. I couldn't have the sine of beta over the cosine of alpha and condense it into tangent. This only happens when the angles inside those trig functions are the same. Again, sine of x divided by cosine of x is equal to tangent of x. So sine of alpha divided by cosine of alpha is technically the tangent of alpha. This is also true for the sine of beta divided by cosine of beta. That's the tangent of beta. And that is actually equal to that other side. And it does verify that identity. Keep in mind that you can utilize these identities as individual steps. You can do algebraic steps in between here. Just make sure that you're not doing anything mathematically inappropriate with any of these steps. Let's take a look at proving another one of the identities that's actually on the identity sheet. Let's look at verifying the tangent of alpha plus beta is equal to the tangent of alpha plus the tangent of beta divided by 1 minus the tangent of alpha tangent of beta. Now this is a relatively hefty problem. All we're actually trying to do is we're trying to say, hey, guess what? We know that these identities are true. Let us utilize these 4 identities to verify this next identity. And that's actually how this entire identity sheet works from this point forward, is we're using previous identities that we now have learned and on our identity sheet to verify and make new identities. So let's see if we can make this new identity based on the previous identities. Again, the first step that we're adding to the new step of verifying identity techniques is changing it so that all the angles inside each trig function are actually the same. Alpha, beta, alpha, beta, alpha plus beta. This one's the one that's different on separating it from this side. So I'm going to change this side tangent of alpha plus beta. Well, I want to change it so that it's no longer alpha plus beta, but here's the trick. For this identity, you're asked to verify it. It's important to understand that you're asked to verify the identity that's on the identity sheet. If you're asked to verify the identity that's on the identity sheet, you can't just utilize that identity. It's not mathematically appropriate. You're asked to prove that this is true, which means that you can't just say, hey, it's on the identity sheet, therefore it's true. So the expectation is you're going to use these previous identities before it to prove that it is true. So what I'm going to have to do is I'm going to have to use the skill that I had with the sine of alpha over the cosine of alpha equaling to the tangent of alpha. I got to do the same thing with this side. I'm actually manipulating what looks like the more simple side first this time. So tangent is the same thing as sine over cosine. And the angles inside of those are going to be the same as what they were inside that tangent. So now we can do this with this side over here as well, but I'm going to hold off on manipulating this side. I'm going to, again, start with this side that has the multiple different angles within one trig function. So the sine of alpha plus beta and the cosine of alpha plus beta. I'm going to take this side and I'm going to work with this side. So this is equal to, I'm unchanging this. I'm going to go ahead and not write that down over and over and over again until I absolutely need to. So the first thing I'm going to do with this side is I'm going to go ahead and change it from tangent to sine over cosine. I'm then going to go ahead and use the sine sum identity and the cosine sum identity and transform those appropriately. So the sine of alpha plus beta is going to be the sine of alpha times the cosine of beta plus, notice the sine again stays the same. I'm going to have the cosine of alpha sine of beta. This is all divided by. The cosine one has the sign change, and we're going to have, in this case, cosine of alpha cosine of beta minus sine of alpha sine of beta. This is where things might seem to get a little bit tricky. Before I move any further, I'm going to look back at what I'm trying to prove it to be. I'm trying to prove it to have tangent of alpha plus the tangent of beta, and it's divided by 1 minus tangent of alpha tangent of beta. This is where you might have to think a little bit deeper into the problem that we're looking at. You'll notice that there's 1, 2, 3, 4 terms in this division. In this division on this side, you'll notice there are 1, 2, 3, 4 terms. You'll notice that the sign plus and the sign plus match up. You'll notice the minus sign also matches up. So what's the kicker here? What's the unique thing that I'm going to have to do to make this thing work? Well, the first thing that I'm going to notice is this right here. I want this term on the bottom to be a 1. That's the one right there. I want that term to be a 1. If I can make that term a 1, then all the other terms, the tangent of alpha, tangent of beta, tangent of alpha, beta, tangent of alpha, tangent of beta, should just simply fall into place. So how do I make this term right here be a 1? Well, that means I need to divide this term by cosine of alpha, cosine of beta. If I can divide this term by the cosine of alpha, cosine of beta, keep in mind, I don't want to change the number of terms, so I don't want to add and subtract things. I want to divide or multiply. So if I divide this term by the cosine of alpha, cosine of beta, that's going to change that term to be a 1. But that means I'm going to have to divide this term by the same thing. I'm also then going to have to divide the top stuff by the same thing. Really, the way that this mathematical term or mathematical step is going to look, it's going to look like I'm taking everything and I'm going to multiply it by 1 over the cosine of alpha, cosine of beta. That's what it should look like. Again, this might be really smooth operating, and it might be difficult for you to see this first time over. But after enough practice and after enough examples of this, you should be able to start taking some of these skills and applying them yourself. Again, doing this is not easy. It takes some time. It takes some effort. I know that this is where I'm headed. I know that this is what I have. I know that the plus sign and the minus sign match up, and I know that I have two terms on top, two terms on bottom, two terms on top, two terms on bottom. Make this a 1, and mathematically everything else should work. So I'm going to distribute this division to this term and this term. I'm going to do the same thing for the top as well. I'm not going to show all that extra stuff. I'm just going to go ahead, as I'm doing it, I'm going to show the simplification. Cosine of alpha, cosine of beta divided by these two terms is going to be 1. So I'm going to have a giant fraction bar, and it's going to be 1, and I'm going to carry down that minus sign. This stuff here is going to be the sine of alpha, sine of beta divided by cosine of alpha, cosine of beta. I'm actually going to write that step out just so that you can see it more clearly. But I'm going to go ahead and simplify some of the stuff on top. Sine of alpha, cosine of beta divided by this. Notice the cosine of beta and the cosine of beta should cancel each other out. I should be left with the sine of alpha divided by the cosine of alpha. The plus sign shouldn't go anywhere. And a similar thing should happen with this one. Notice the cosine of alpha on top and the cosine of alpha on the bottom should cancel each other out. And I'll be left with sine of beta over the cosine of beta. One last step. This should end up being, again, sine of alpha over the cosine of alpha is the tangent of alpha plus the tangent of beta divided by 1 minus, this is very similar to a previous set of details that we did, such that this is going to be sine alpha over cosine of alpha is tangent of alpha, and then tangent of beta. And sure enough, this is the same thing as that side up there. So notice how we worked with the side that happened to have more or different angle interior identity. We can manipulate sines and cosines. We can then transform based on the sum and difference identities. We can then do some algebraic manipulation and get it to be the exact same thing. That's the goal for most of these steps.